Okay, welcome to the next video here on grain boundaries. Here, what we're addressing are two-dimensional defects. So we're building off the idea that a one-dimensional defect could be represented by, say, for example, some sort of a line defect. And in this case, you can see here the defect will curve on itself in the plane, and this gives rise to the two-dimensional aspects of this defect. So in our diagram at left, we have isolated crystallites, which are, of course, represented nicely by our unit cells and all the calculations that we've done there. And you can see at some point there exists a boundary between that crystallite and the neighboring one. Here. And so the boundary between the two is known as the grain boundary. So a crystallite, therefore, is also called a grain. And obviously the boundary between grains is the grain boundary. Okay, so in these other diagrams, hopefully you can recognize some grains. So in the kind of gold and gray image atop, we've got a boundary kind of in between the two, and you can see that we have regular array above and below, and so we've got the boundary between two grains shown there, and the number of grains in view down below appears to be on the order of 3. So there's a grain boundary here and another one about here, and so we can see the boundary between 3 grains or 3 crystallites, again all represented nicely by their unit cell. Okay. The specific sort of architecture at the grain boundary, it can be very complex, but in the scenario where we have a simple case where 2 distinct crystallites or grains are separated by what's called a tilt boundary, we have the concepts of our edge dislocations taking the space of that's located in the grain boundary. Okay, so you can see here our edge dislocations, which again we've represented with the sort of symbol, the perpendicular symbol that we've seen, and a Berger's vector that we know how to determine are characteristic of this edge dislocation. And we have a nice equation here for determining the average distance between those edge dislocation sites where that one-dimensional error coming out of the page at that sort of perpendicular system or symbol exists. Okay, so the average distance between that will be the Berger's vector, okay, typically in nanometers. Vector. So that'll have units of nanometers. And therefore, as would be the average distance between those edge dislocations. Distance between edge dislocations. And again, nanometers would be the result there, which means that our theta, the tilt angle between these crystallites, the angle at which they're offset from one another, would be in radians. Okay, so again, we recognize that there are pi radians in 180 degrees, and that would help us there. Okay, so this tilt grain boundary can be quantified further with this geometric relationship, if you will. Okay, so here's a electron micrograph at 100 times magnification of a low carbon steel, and some surface processing has been done ahead of time, so some polishing and etching to really emphasize that what we are looking at are grain boundaries, not scratches, score marks, or other blemishes in the surface. So we work hard to prepare the surface for characterization by this technique to later have confidence that we are describing grain boundaries. Okay, so here you see the black lines clearly have a different contrast than the surface of a crystallite that is regular in its arrangement of atoms, and we have sort of errors in that occur at the grain boundary. Okay, and again, this is a two-dimensional defect as the grain boundary turns within the plane to ultimately loop and connect to other grain boundaries. Okay, so I think we've addressed most of this. You'll see that generally there's each grain is not regular in structure, and the grain boundary is therefore quite complex and arbitrary, and a lot of these features can be determined by the sample history, the thermal history that has gone into the sample, or pressure history that has gone into the sample. Okay, so more on that characterization technique. So optical microscopy is typical here to view grains, which can be often on the order of millimeters in size. So optical microscopy is appropriate for characterizing the size of grains. And so this technique is useful for viewing things up to about 2,000 times magnification, or where features are on the order of about 500 nanometers and up. Okay, so long as features are on the order of the wavelengths of light, then we'll be able to find them by optical microscopy. We mentioned that polishing is necessary for the surface, so this is going to remove scratches and blemishes and other things, and etching is sometimes used to really make sure that what we are seeing at a surface is a function of atom density. And so you'll recall our ideas for planar atomic density. And so hopefully it connects for you that the more atoms that are present in a unit area of plane of the lattice, that's going to be an opportunity for us to get contrast in the optical microscopy exercise for characterizing that surface. So imagine, if you will, some of these crystallites that are present. There's sort of 5 shown here in the image at right, 3 of which have sort of atomic planes cartooned onto them through these blue lines. And with a properly polished and etched surface, using both physical and chemical polishing techniques, you can see here that the surface texture, which is set by the atomic planar density, will allow for incoming light to reflect off of that surface differently. Okay, so depending on what atoms are present, their arrangement and their density in the plane, we get contrast this way. So here you can see down below a result for copper zinc alloy, or brass as you might know it, showing many different grains of this solid solution of copper and zinc. And you can see here that we are getting black, whites, and grays owing to the different crystallographic planes that are present at the nicely polished surface. Okay, note the scale here. So we are about 0.75 millimeters for the whole image, so very high magnification. This is something like the dimensions of your lead in your mechanical pencil. Okay, so talking now about grain density, what we want to try to do is develop a quantified approach to counting the number of grains associated with an image. Okay, so here's a couple of arbitrary kind of binary images, only black and white. To help us, you can see the grains are all represented by white areas. So these grains are, of course, crystallites. And we have kind of large crystallites in image A, and we walk to smaller crystallites down into image D. So looking at the scale here, if we have a scale of about 1 inch in these arbitrary images there, what we try to do to count grains is to quantify how many of them exist in a square inch. So we kind of take that scale and we impose it over top of an area, and we estimate how many grains are present in that area. So in image A, I would say there are an average of 1 full grain per square inch. When we do the same for image B, we'll see that there are roughly about 2 grains per square inch there. When we do the same for image C, on average there might be something like 4 grains per square inch there. And then in image D, with far smaller crystallites present, much smaller crystallites present, we're going to see something like 8 grains present in the same unit area. Okay, so this idea of simply counting the number of grains that exist in a unit area is the initial basis for quantifying a grain density value that we'll show you in a moment. Note here that these images are at 100 times magnification, and the basic form of calculating grain density, as we'll see, is going to rely on images at this magnification. Clearly, if we change the magnification, I am going to see different grain count per unit area if I haven't accounted for magnification. Okay, so here we have the American Society for Testing and Materials has come up with an equation for us here. So we have the ASTM grain size number represented as N. Okay, so this is the characteristic that we calculate based on information that we just had, which was estimating the number of grains per square inch, provided that we have an image acquired at 100 times magnification. Okay, so you'll note that in your textbook, this equation is presented to you outside of the ASTM format, so I'll bring that to your attention now and later in the slide. This is presented to you in your textbook as 2 to the G minus 1. And you can see here that lowercase n is taking place of capital G in your textbook's version of this ASTM equation. Okay, so based on what we saw earlier, we know that we can estimate this just from the images, and so in solving for the exponent term n, we acquire the ASTM grain size number. And this is a characteristic that one reports for the grains associated with a particular material. Okay, so that top half of the slide here is addressing a very specific set of images. They're required at 100 times magnification. Now, should you be able to view grains only at a different magnification, larger or smaller in the magnification value, this equation thankfully can be modified. Okay, so here we would count the grains per square inch at a different magnification value and take into account that magnification value. So we would do 100 divided by that magnification value, and then we can adapt the top equation to present the bottom one. Okay, so going back to what we have here, we know that the number of grains per square inch is equal to 2n minus 1. And so in order to get an answer of 1 for the number of grains per square inch, the outcome for the first entry would be 1. Okay, so an exponent n of 1 would give us the proper grain size per square inch, number of grains per square inch. Okay, and so hopefully you follow that this equation becomes quite useful, as we can now report a simple grain density number as we quantify images by this technique. Okay, so here's some data from an old resource here where we have large a grain size number. So this was our N value, and here we have the number of grains per square inch for images acquired at 100 times magnification. And here you can see the result of solving for that exponent term lowercase n in our equation here. Okay, so putting a little bit more of a visual to this, so we saw these were large grains, large crystallites neighboring up against large crystallites at the top, and then as we go down, we have small crystallites, and many of them meeting up against each other, separated by grain boundaries. And so it follows, therefore, that as the grain size increases, the ASTM grain size decreases. Okay, so if crystallite size is increasing, we see that the ASTM grain size number decreases. Okay, very good. So the basis for this equation, if you want, is putting a bit of a fractal approach or model between the two, between actual images and a sort of honeycomb type lattice to occupy the area of the image. So that's the fundamental basis for this equation, and how we kind of carve up general area to give this. So the number, the ASTM grain size number is evolved from this concept. Okay, so maybe this diagram helps you kind of visualize how we're representing the general number of grains per unit area through these kind of neighboring honeycombs that are regular in structure, representing what we would have in a much more disordered actual image down below. Okay, very good. So again, just to emphasize, your textbook presents to you that same equation here, a little bit outside of the ASTM format that we're used to. So I've introduced it to you according to that, where lowercase n is in place of capital G. Okay, the last sort of topic of Chapter 4 was considering the difference between crystalline and non-crystalline material. So this is brought up to you in the form of the crystal of silicon and oxygen, or silica. And so silica, it can exist in a really regular format where we have well-defined repeating units. Okay, so you see one highlighted here. So this pattern can repeat itself in 3 dimensions, and we have interstitial sites in the middle of this pattern. And so this crystalline oxide is very regular in its structure. Okay, in the case of silica, this is the basis for quartz, which has a really well-defined lattice of its silicon and oxygen atoms. Silica can also be rendered non-crystalline or amorphous, where here you see the arrangement of atoms into their connected format is more randomized. Okay, so the regular repeat that we see at left only exists in a few spots, and the overall kind of atoms contributing to any rings that we see in the connectivity of the material are more random in size. Okay, so there's a more random pattern in the non-crystal oxide, as you see emphasized here in these blue features. Okay, so non-crystalline oxides are also synonymous with amorphous rather than the crystalline format. And again, depending on processing and or the mode of making the material, the synthesis, if you will, we can access either crystalline or amorphous oxides. In this case, silicon, its crystal format, or in its amorphous format. Okay, so with that, we'll end. That was a short video on some two-dimensional defects called grain boundaries, and we'll continue into next week with some topics from chapter 5 and 6. Thank you.